So good morning, everyone, and welcome to the lecture. This is lecture number 2, and we are dealing with semiconductors. Well, in the previous class, we had seen what a semiconductor is. We had seen the type of semiconductors. We had seen their intrinsic and extrinsic semiconductors, and we had also seen the two types of extrinsic semiconductors, the p type where the majority charge carrier are holes, and the n type where the majority charge carrier are the electrons. In today's class we will move ahead and we will venture into the part where we will be dealing with the combination of a P and N type, and a combination of P and N type is known as PN junction diode. So that is the heading for today's class, PN junction diode. Now, what do you mean by a PN junction diode? Anyone, any idea? What is a PN junction diode? Have you heard the term PN junction diode ever up till now? Have you heard the term PN junction or PN junction diode or diode? No one has heard this term? Yes or no? Have you heard the term PN junction diode? Okay. So what is a PN junction diode? For P-type semiconductor, you have a P-type semiconductor and it is joined to a N-type semiconductor. This combination is known as, or this arrangement is known as a PN junction diode. A PN junction diode is a simple semiconductor device, the simplest semiconductor device, the simplest way in which you can use a semiconductor as a device is a combination of P and N type. It is a crystal having acceptor impurities in one region, P type, acceptor type in one region, and donor impurities in the other region. The boundary between the two is, my dear friends, known as a P-N junction. So this is as simple as it gets. The combination is known as P-N junction, and this is how the symbol of a P-N junction is: an arrow and one danda, one vertical line. That arrow is for P, this is for P, and you can think of this danda as for N. P-N junction diode. This is the symbol for a P-N junction diode. Do we understand this? I'll give you a minute to note this down. Then the next thing is how we actually make a PN junction. This is just basic theory, may not come in exam. You must just know for your common knowledge that there are two methods of creating a PN junction or PN junction diode. One is known as the alloy method. In this alloy method, the impurity is placed over the silicon or germanium crystal and it is melted. So it becomes something like this. As you can see here, no one is going to ask you. This is how it is made. This is known as the alloy method. And the next one is the diffusion method, in which a heated p-type semiconductor is kept in a chamber or evacuated chamber where you have vapors of pentavalent impurity or the reverse. And that is how this PN junction diode is formed. The diffusion method is better than the alloy method. This is what it is used. These are the two methods, the alloy method and the diffusion method. I'll give you a minute to quickly note down what is, just you can write the method alloy and junction, alloy and diffusion, and that is more than enough. I'll give you a minute. So we move ahead and we understand this concept of depletion layer. Now what is this depletion layer? As soon as you have a p-n junction which is formed, let us say on the left hand side you have a p-type. A p-type has acceptor impurity, whereas an n-type has donor impurity which can donate electron. This one can accept electron. Now as soon as a p-n junction is formed, what happens? There is a difference in the concentration level between the p-type and n-type. Do we understand this? In the p-type we have more holes and in the n-type we have more electrons. So what will happen? There are more holes here, so holes will try to move to the n region and electrons will try to move to the p region. Yes or no? Now because of this diffusion of electrons, there would be an electric field which is generated from the n side to the p side, which opposes this diffusion process. Now what happens because of this opposition? This diffusion ultimately stops, and it gives rise to a region, this yellow region. I hope you can see this yellow color. You can see this yellow region where what happens, the n-type and p-type, they cancel out each other, and in this region there is effectively no free electron or hole. This region is known as the depletion region. Do we understand what do you mean by depletion region? Whenever a p-n junction is formed, because of difference in concentration on both sides, holes jump from p to n, electron jump from n to p. Because of this, there is a region formed between the p and n type where there are no holes and electrons. This region is known as the depletion region. Do we understand this?
Yes, sir.
I'll give you a minute. You don't have to note down all the things. You just have to understand that there is a region. Do we understand this? And write it in your language. What has happened? So this is again illustrating the same fact. What is depletion layer? Because of diffusion of electrons from p type to n type, n type to p type, negative layer comes near to the p type and a positive layer is formed near to the n type. There is no free electron or hole in this region. This region is known as the depletion region or the depletion layer. What are the important points that you must remember? Because for this depletion region, the thickness of this depletion region is very small. The width of this depletion layer is inversely proportional to doping. More you dope, less will be the layer. It is directly proportional to temperature. This p-n junction diode can be thought of as a capacitor, in which the depletion layer acts as a dielectric. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. Note down the important points, draw the graph. And what you have to understand in this graph is this VB. You see this potential difference?
Yes.
We will get to know about this potential difference in the next page. Note it down. Now, because of this migration of holes from P to N and electrons from N to P, as I told you, there is a potential difference created between the p-type and the n-type. This potential difference created between the p and n-type is known as potential barrier. For germanium, this potential barrier is 0.3 volt. For silicon, it is 0.7 volt. On an average, it is somewhere around 0.5 volts. Because of this, there is an electric field which is produced in the space, and this electric field will be given by V by D, where D is the width of this depletion zone. Do we understand this?
Yes, sir.
This electric field prevents the further crossing over of the charges from one side to the other side. Do we understand this?
Yes, sir.
So once this depletion layer is created, my dear friends, afterwards there cannot be any shifting of holes and electrons across this, because they will not be able to overcome the potential barrier. Are we able to understand this?
Yes, sir.
Now, if we draw a graph between potential and distance across this depletion zone, the graph of potential would look like this. The graph of charge density, when I say charge density, I mean charge per unit area and electric field. I'll show you all the three graphs. These are the three graphs that can be drawn of three different things. How potential changes across the potential barrier. Remember, from here to here, the distance is D, which is the width of the of the of the potential of the depletion zone. I will show you in a separate graph how this thing looks with a PN junction. Right now, just draw this. These graphs can very easily appear in one of the papers that you have. So I'll give you a minute to note this down. Now this is the same diagram, but showing you with the PN junction. As you can see, this entire, oops, you will not see this. This entire green region is the depletion zone. Do we understand this?
Yes, sir.
Great. Then here you have the potential difference. We call it the barrier voltage or the barrier potential VB. Do we see this?
Yes, sir.
Then these are the graphs. This graph is the graph of charge density. This graph is the graph of electric field, and this graph is the graph of potential difference between the 2 points. Do we understand this?
Yes, sir.
I'll give you a minute. If you want to draw it with this, you can also draw it with this just to understand, or you can just mark it in the previous graph as I had marked that the distance between the 2 points is the potential barrier or the depletion zone. I'll give you a minute to note this down. Now this is a question that comes in a PN junction with open ends. What do I mean by open ends? It is not connected to anything. It's just a PN junction as the one that we just showed. In a PN junction with open ends, which of the following options are correct? This is a question from JEE Advanced, multiple choice. So more than two options can be correct. I'll give you a minute to give me the correct answer. So what is the correct answer?
Option 2 and 3, sir.
The correct options are option 3 and option 4. Once a p-n junction diode is formed, once a barrier is formed, then the electrons cannot jump from one side to the other side or holes from one side to the other side. Option number 1 and 2 are not correct. Option number 3, there is no net flow of charge across the potential barrier. Yes, there is a constant electric field. I just gave you a formula for that electric field also. Anyways, this is the next question. And I hope that I can get an answer to this one. A potential barrier of 0.5 volt exists across a PN junction. Its depletion region is 5 into 10 raised to the power minus 7 meters wide. What is the intensity of electric field in this region? You have a minute to win it. Option 2, and how do we get that option? Electric field is V divided by D, so it is 0.5 divided by 5 into 10 raised to the power minus 7 volt per meter. And my dear friends, the answer that I have is option number 1. I hope that you know how to divide. And I won't further comment on it because the more I comment, the worse you get. We'll move on to the next heading, and the next heading is known as diffusion and drift current. Diffusion and drift current. What do you mean by diffusion and drift current? Now, diffusion current. Now remember that there is a difference in the concentration of holes and electrons on the both sides. On the p side, we have more holes. On the n side, you have more electrons. Now there would be certain holes or electrons which have a very high kinetic energy. Now these very energetic holes or electrons can move. Holes will move from p to n. Electrons can move from n to p. Because of this, there will be a current that flows. The direction of this current will be from p to n type, and this current is known as ID or IDF. The diffusion current, IDF. IDF. So diffusion current, remember, it's from p side to n side. Number 1, it is from p to n. Number 2, it is because of difference in concentration. These are the two things that you must remember about diffusion current. This can very well appear as a question in your exam. You are weak in calculations, you are weak in remembering things, but still I hope that God will be merciful on you, and you would be able to remember some of the things that we are discussing here, because same things are going to come in the examination hall. Now, because of next thing, thermal collisions or thermal energy, these electron and hole pair are continuously created because of this thermal energy, because of thermal collision or increase in temperature. You can also add or increase or rise in temperature. There is always electron hole pair created. Now, because of this creation, there is a constant flow of electrons towards the n side and holes towards the p side. Because of this, there is a current from n to the p side. This current is known as the drift current, dr. So what are the two things that you must remember about the drift current? It is from n to p. Number 2, it is because of thermal agitation or thermal collision or increase in temperature. Because of increase in temperature, this drift this drift current is produced. In steady state, you must remember that the drift current and the diffusion current becomes equal and opposite, and therefore the net current, my dear friends, becomes zero. The net current becomes zero. The second thing that you must also write here as a second point is that when no external source is connected, that means they have open ends, no external source is connected, PN junction diode is free, not connected to anything, isolated. This diode is known as unbiased. Please remember, beta, from 15 days or 20 days from now on, 30 days, you will be appearing in your exams. One of these things is going to come. Please, I beg of you, remember them. Please, as a sincere request. You put in so much of hard work, and I hope that you get something out of that hard work. I'll give you 2 minutes to note this down. Same thing may come in the exam. You never know. As I said before, if you have a PN junction diode which is not connected to anything or it is isolated, we call it unbiased. But if you connect it to a battery, well, we call it biased. There are two types of biasing that can be done. They are known as forward biasing or reverse biasing. What is forward biasing? If you connect this P type to the positive terminal, once you connect P type to the positive terminal and gets connected to the negative terminal, this type of biasing is known as forward biasing. This type of biasing is known as forward biasing. If you change the voltage, the forward voltage, and you draw a graph between the voltage and the current, this graph, my dear friends, would look like this. And remember, this is not a straight line between I and V. That means it does not follow Ohm's law. I is not directly proportional to V. It is non-ohmic material. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. Then we again look at the diagram. You have already drawn the diagram, so you may not draw it again. You can note down the important points of this forward biasing. In forward biasing, the depletion layer, the width of the depletion layer decreases. Depletion layer becomes less. Why depletion layer becomes less? Because the forward bias opposes the potential barrier. Therefore, the depletion layer decreases and a current is set up from P type to the N type. Since the depletion layer becomes less, the resistance offered also becomes less. It comes in the range of 25 to 100 ohms, which is less. There is a voltage which is known as the cut-in or the knee voltage. Do you see this, the cut-in or the knee voltage? This is the voltage at which the current starts to increase rapidly. Current is not directly proportional to V, so this is a non-ohmic device. Do we understand this?
Yes, sir.
You have 2 minutes to note this down. Remember, in this chapter, everything is theoretical. The next type of biasing would be known as reverse biasing. And as you can see, what will happen in a reverse bias, P type is connected to the negative and N type is connected to the positive. So what happens? It increases the potential barrier and the electrons or the holes will not have sufficient energy, because the applied electric field is opposing their motion, there would not be any current flowing in the circuit. Effectively, there would be almost no current which will be flowing through the PN junction because of reverse biasing. So one thing we can very clearly say, a PN junction diode can only conduct a PN junction diode can only conduct a PN junction diode can only conduct or function or allow current in one direction. And in which direction it allows current? It only allows current when it is forward biased. PN junction diode only allows current. PN diode only allows current. When does it allow current?
Forward bias.
When it is forward biased. In reverse bias, it will never allow current to flow. I'll give you a minute to note down all these important points. Well done, sir. Then we look at the reverse bias characteristics. What do you mean by reverse bias characteristic? Is that we find out what is the value of current for different applied voltages. Points to be remembered: in reverse biasing, the width of the depletion layer increases, resistance offered becomes very high. Reverse bias suppose the potential barrier, so effectively the current becomes zero. A very small reverse current, the drift current, may exist because of drifting. Drift current, diffusion current. So very small amount of drift current does exist here. Breakdown voltage, when the reverse voltage, if we keep on increasing the reverse voltage, at some point it will break down. Boom! The junction breaks down. That voltage is known as breakdown voltage. I hope you can see the breakdown voltage. Yes or no?
Yes, sir.
You have 2 minutes to note it down. Remember, semiconductor is all about these points. The same thing written in a tabular form for quick revision. Forward biasing on the left hand side. Oops. Forward biasing on the left hand side and reverse biasing on the right hand side. Here P positive is connected. Oops, wrong color. Here P positive is connected to positive and N negative is connected to the negative terminal. The width of a depletion zone decreases, the forward resistance becomes very less, a forward current is established. Here on the other side, P is connected to negative and N is connected to positive. The width of the depletion increases, forward resistance is more. There is potentially no current, diffusion current because of the majority carrier, but drift current can exist. You have 2 minutes to note it down. The next 2 points we have also discussed. We have a cut-in or the knee voltage. We have a breakdown voltage here. These are the characteristics, the reverse, the forward characteristic. You can see the diffusion current is on this side, the drift current is on this side, the net current will be on this side. It will be a good current. On the other hand, you see here the diffusion current is like this. The drift current would be more here, and therefore the net current will be because of, in other ways, what we say here, the current is because of minority charge carriers. The current in reverse biasing is because of minority carriers. The current in forward bias is because of majority carriers, majority charge carriers. After this, leave 2 or 3 spaces. There would be some other things that we might add here. I'm giving you 2 minutes. If you want to note it down, note it down. Now we have seen what we call as the breakdown in reverse characteristic when we have reverse biased PN junction. At some point, as you see, it breaks down. Do we remember this breaking down? At this point, it breaks down. This is known as the breakdown voltage. Do we remember this?
Yes.
Now, this breakdown can be of two types. Two types this breakdown can be. What are the two types of breakdown? Well, the first type of breakdown is known as the avalanche breakdown. I'm giving you the entire theory, but you might not have to write the entire thing. Avalanche breakdown, you just have to note the important points of this avalanche breakdown, and I will give you in a tabular form as well. This occurs in lightly doped junction. This occurs in lightly doped junction, and this happens because of high reverse bias and breaking down of covalent bonds. When the reverse voltage is made very high, the covalent bonds may break. This type of breakdown is known as avalanche breakdown, and it is shown by the section CD of your graph. You remember that section CD? This section, my dear friends. We. This is your avalanche breakdown. This is your avalanche breakdown. Do we understand this? You don't have to note the entire Ramayana. No one is going to ask you why did Shurpanakha came and tried to entice Ram and Lakshman. They're only going to ask you who was Ram and who was Lakshman, probably. The next type of breakdown, that means you just need to note the important points. You don't have to know the entire Ramayana. Who was Shabri and why did she give Jhuta bear to Bhagwan Ram? So no one is going to ask you the finer details. The only thing they are going to ask you is the broader details. The next one is known as a Zener breakdown. Now, what do you mean by Zener breakdown? Remember the important points. It occurs in highly doped junction. It occurs in highly doped junction. Now, when these highly doped junctions are there, and when you increase the electric field, you will have a breakdown, and that breakdown is known as the Zener breakdown. Do we understand this?
Yes, sir.
Two types of breakdown. The avalanche breakdown, which happens in low doping cases. The Zener breakdown, which happens in high doping cases. I will give you, have you noted it down? I will give you a table which
Yes, sir.
Summarizes both the facts together. So these are the facts summarized in a table. On the left hand side, my dear friend, you have the Zener breakdown, and on the right side, you have the avalanche breakdown. The avalanche breakdown happens because of the collision of minorities, and the covalent bond depletes, and it happens in low doping and in PN junction having thick depletion layer. This is because of the heating effect. Here, the covalent bond self-break due to high electric field. It is in a region of high doping and thin depletion layer. Here, the PN junction is not damaged permanently. Here, it is damaged permanently. Dabak, it goes away. Any one of these points may appear in your exam, my dear friends. Then we move ahead into a topic which I think we had discussed when we were discussing Ohm's law, something known as the dynamic resistance. The current voltage graph is not a straight line and it does not follow Ohm's law. Therefore, we can define the resistance which is known as the dynamic resistance. Small change in voltage divided by the small current. Do we understand this?
Yes.
This is known as the dynamic resistance of a junction diode. I'll give you a minute to note it down. So whenever someone talks about the resistance of a diode, he is talking about the dynamic resistance. Small change in voltage between 2 points divided by the small change in current between the 2 points will give you a resistance. That resistance is known as the dynamic resistance. You have 2 minutes to note it down fast. So as I told, there might be some things that you would have to add in this forward and reverse biasing. We talked about the resistance is very small. That resistance is actually your known as forward resistance. Delta VF, forward voltage divided by delta I, the change in forward current, that is approximately equal to 100 ohms. Here we talk about the reverse resistance, change in reverse voltage divided by change in reverse current. The next thing is the forward current equation. This is not in your course, but if they ask you, this is the forward current equation, and the forward current is equal to I naught e to the power k qv by kt, where what is I naught? I naught is the current at the breakdown at the knee voltage. I naught is the current at the knee voltage, and here I naught is the current at the breakdown voltage. Do we understand this?
Yes.
So this in the reverse case, reverse biasing, this I will always be equal to minus I naught, minus only indicating the direction is reversed. Here, in case of forward biasing, this current will raise exponentially, and that is what you have to note down. I'll give you a minute to note this down. Then we can combine both the graphs together, and we have something which is known as the characteristic, not the forward or reverse, but both of them combined. Characteristics of a PN junction diode. You know what is a PN junction, P and N. You know the symbol. You know what happens in forward bias. You know what happens in reverse bias. So basically, if you talk about this diode as a switch, in the forward biasing, it acts as a closed switch. It allows current. In reverse biasing, it acts as an off switch which will not allow current to flow. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. Well, then we have this question. In this question, you have to tell me which of the following diodes are forward bias. You'll have 2 minutes to give me the answer. And the answer is definitely option 2. In this first case, you can see this is reverse bias, yes or no?
Yes.
P has to be connected to more positive. This is forward biased. This is reverse bias. This is forward bias, and this is forward bias. Everyone understands this, yes or no?
Yes.
Let's see. If you can give the answer to the next one, and this is the next one. Two ideal capacitors A and B are charged to the same potential V and are connected to two circuits at time t is equal to 0. The charges on the capacitor at time t is equal to CR is how much? Option 2 is the correct answer. In the first case, case number 1, it will behave as a switch. So both the capacitor plates would be connected. Q is equal to Q naught e to the power minus t by RC. The capacitor would get discharged, but in case number 2, it will behave as an open circuit. The plates of the capacitor will not be connected. Therefore, the charge on the capacitor will remain constant. And therefore, only the correct option has to be option number 2. Do we understand this?
Yes, sir.
Everyone understands this?
Yes.
Or this is going above our head saying bye bye, bye bye, bye bye, bye bye. I'm going bye bye. Here comes the next one. Any one of these questions will land up in your paper. What is the current shown in the circuit shown below? You have 2 minutes to give me the answer. And the answer is option 1. Why is the answer option 1?
Reverse bias, sir. Because it is in reverse bias.
Because it is in reverse bias, my dear friends. It cannot conduct whatever we do. This gentleman cannot conduct, and therefore the answer has to be there could not be any current flowing in the circuit. Everyone is able to understand this?
Yes.
This is the next question. You may have a similar question in your exam. A 2-volt battery is connected across 2 points A and B. So they have not drawn the battery. If you want, you can draw a 2-volt battery here. As shown in the figure, assuming that the resistance of each diode is 0 in forward bias and infinity in reverse bias, the current supplied by the battery when its positive terminal is connected to A is how much? You have 2 minutes. Well done. The current would be 0.2 amperes, and the reason is if I call this current as I, if I call this current as I1, and if I call this current as I2, what will be the value of I1, the current in this? How much current will flow in this branch?
Sure. 0, sir.
The current in this branch would be 0 because this diode would be reverse bias. No current can flow. So I current will be equal to I2 current and will be flowing in this way in the green path. The total potential, the total battery is 2 volt. The total resistance is 10 ohms. Therefore, the total current flowing to the battery or whatever will be zero point 0.2 amps. These are the simplest question that would be asked in an examination hall. Do we understand this?
Yes, sir.
There is one more question. Remember, one of these questions, maybe with same data, will appear in your exam. Don't be surprised. Simple question only appear from this particular chapter. This is the next question. Current in the circuit is how much? So again, as you can see, in this branch and in this branch, in which branch will the current flow?
Green branch.
In the
Green color branch.
in the green color branch, current will flow, and in the pink branch, because it is reverse bias, it will not flow. Total resistance is 50 ohms, and the total voltage is 5 volt. So the answer has to be current can only flow in this path because of forward biasing, and the answer would be 5 by 50. It's very simple to understand this. The next question would be like this. A diode used in the circuit shown in the figure has a constant voltage drop of 0.5 volt at all currents and a maximum power rating of 100 milliwatts. What should be the value of resistance R connected in series for the diode to obtain maximum current? Let's see if you can give me the answer for this one. We have to find out the value of this resistance R. As you know, the potential difference which is applied is 1.5 volt. You can also see that 0.5 volt is to be there across the diode. So that tells us that the potential drop across the resistor R will be how much?
0.5.
Yes, it would be 1 volt. The potential drop across the resistor R would be 1 volt. The potential drop across the diode is 0.5 volt, and therefore the total potential drop becomes 1.5 volt. I have to find out the current. I have to find out the resistance. V is equal to IR. That is the only formula that we have studied. So the resistance will be V divided by I. If I somehow know the value of I would be able to find out the value of the resistance R. How will I find out the value of I? To find out the value of I, you must remember that voltage drop across the diode is given as 0.5 volt, and the power, the maximum power that will come from maximum current is given as 100 millivolt. The other formula that we have studied, if you would recollect, is power is equal to V into I. From there, I can calculate the current in the circuit. Power is 100 milliwatts, 10 raised to the power minus 3 divided by 0.5. That would give me the current. The current that I will get would be 0.2 amperes. I put the value of current from here to in this equation. I will get the value of resistance, my dear friends, as 1 divided by 0.2, my dear friends. And the answer in that case would come as 5 ohms. So that is how we have done this. How we have done this, let me repeat. The total voltage drop is 1.5 volt. The battery voltage is 1.5 volt. The voltage drop across the diode is 0.5. Therefore, the voltage drop across the resistor becomes 1 volt. If I know the current, I will be able to find out the resistance. How do I know the current? Power of the diode is given. Power is VI. I know V. I can calculate I. 0.2 amperes is I. I get the value of resistance from V is equal to IR. I'll give you 2 minutes to note this down. Then this is the next question. The same question put in a different way. Assume that the junction diode in the following circuit requires a minimum current of 1 milliamp to keep it above the knee point. The IV characteristics of the curve. The knee point of the IV characteristics. Also assume that the voltage across the diode is independent of current above the knee point. Above the knee point, the voltage remains same. Current just drastically increase. If VB, the battery voltage is 5 volt, what should be the minimum value of R so that the voltage is above the knee point? I hope you have understood the question, and I'll give you 2 minutes to give me the answer. Option 1 is the correct option. Remember, this voltage across this is given as 5 volts. The voltage across the diode is 0.7. From there, you can understand that the voltage across the resistor R will be 4.7 volt.
4.3.
Sorry, 4.3 volt. You know the current is 1 milliamp, so you end up with the answer 4.3 kilo ohm. That is how you have to do this. Do we understand this?
Yes.
One more, the last question in this category, and it comes like this. The IV characteristics of a p-n junction diode is shown in the figure. Find the approximate dynamic resistance. Told you about dynamic resistance. Find the approximate dynamic resistance of a PN junction when a forward bias of 1 volt is applied. Number 2, when a forward bias of 2 volt is applied. So when we have to find it out for the first case, case A, in case A, the voltage is 1 volt, so you have to change the voltage. Remember, the dynamic resistance in all these cases is change in voltage divided by change in current. So at 1 volt of forward bias, you are going to change the voltage. And as you can see, the voltage is changed by 0.2 volt. Do we see this? Yes or no?
Yes, sir.
And the current changes by 5 milliamps. Do we see this here on this side?
Yes, sir.
So the dynamic resistance becomes 0.2 divided by 5 amps. It becomes 40 ohm. In the next case, case B, again the dynamic resistance is change in voltage divided by change in current. Now we must look at the change in voltage here and the change in current from here to here. Do we see this?
Yes, sir.
If you see this, my dear friends, then it is good. Change in voltage is 0.1 volt, but the change in current is 400 milliamps. Here I have written 5 amps. I should not have written 5 amps. I should have written 5 milliamps. Milliamps. And we end up with our answer. Here the answer, if you divide it correctly, would be 0.25 ohm. So whenever a question comes for dynamic resistor, this is how we must solve it. Do we understand this?
Yes, sir.
Everyone understands this.
Yes.
Then we come to the next heading, and the next heading is known as PN junction as a rectifier. What is a rectifier? Anyone knows what is a rectifier? Anyone has heard the term rectifier? A rectifier is an electronic device that converts alternating current or voltage into DC current or DC voltage. Now, how we can use this PN junction diode as a rectifier? In the forward biasing, it will allow current to flow, but in reverse biasing, it will not allow current to flow. So in one cycle, it will allow current to flow. In the other cycle, it will not allow current to flow, and therefore you can use this PN junction diode as a rectifier. Yes or no? No, yes. Do we
Yes.
understand this?
Yes.
Now this PN junction diode can be used as a half wave rectifier or it can be used as a full wave rectifier. What is a half wave and what is a full wave rectifier? In a half wave rectifier, it only allows half of the wave to go and it does not allow the other half to go of an AC circuit. This is a half wave rectifier. You have primary and secondary. On the primary side, you have AC voltage. Do we see this, my dear friends? And on the secondary side, you have just put a single diode. Now what will happen? In the positive cycle, when this end is positive and this end is negative, it will transmit. In the other half cycle, it will not transmit. Do we understand this?
Yes, sir.
So it will not transmit, so it will behave as a half wave rectifier. Do we understand this?
Yes, sir.
Everyone understands this. Everyone understands this. On input, we have AC, which varies. On the other side, we have fluctuating DC, which changes its value, but it does not change its direction. Do we understand this? I'll give you a minute to note this down. Well, if you want to understand it, this is how you can understand it. During the one cycle, this is positive and this is negative. So you can see current will flow across the load. Do you see this load here? Current will flow across the load from A to B. But in the other cycle, this will become negative. Other half, it will become positive. It will not conduct, and therefore you will have this vacancy over here. Do we see this? Yes or no?
Yes.
What are the things that you must remember? During the positive high cycle, the diode is forward bias and a current is obtained. During the reverse cycle, the next half, it is not obtained. The output voltage is obtained across the load. It is not constant but pulsating. It is a mixture of AC and DC. The RMS output is I naught by 2 and VRMS is V naught by 2 because it becomes half. We understand this. Efficiency of the cycle, we will see it in detail, is 40%. The ripple frequency omega is same that as of omega. That means the angular frequency of both AC and DC is same. Do we understand this for half wave rectifier?
Yes, sir.
Everyone understand this? Can I have raise of hands? Because this is going to end up in your examination paper exactly like this. You should not be found wanting at that stage. Give you a minute to note this down. Then we come to PN junction diode as a full wave rectifier. For full wave rectifier, we need two diodes. This is sometimes also known as center tap, because a tapping is taken from the center of this. Now what happens in one half cycle, and we will show it in the next diagram. This will be positive and this will be negative. So D1 will conduct and D2 will not conduct. Do we understand this?
Yes, sir.
In the second half cycle, this will become negative and this will become positive. D2 will conduct and D1 will not conduct. But whatever happens, my dear friends, the current in the load always goes in one direction. Do we see this?
Yes.
No matter what happens, the current in the load is always going in the first direction. In the first case, it is conducted by D1. In the second case, it is conducted by D2. This is a fluctuating DC, and this type of rectifier is known as a full wave rectifier with a center tapping. Why do you understand? Why do you call it center tapping? Tapping taken from the center. Do we understand this?
Yes, sir.
To give you a minute to win it. Then we can see the same thing in this diagram. If you want to understand, during one half, D1 is forward biased, D2 is reverse biased. The output signal is due to D1 only. In second case, this is negative and this is positive. So D1 is reverse and D2 is forward. The output signal is due to due to D2. This is a fluctuating DC. When you put a filter, it will become, I'll tell you what is a filter. The output voltage is across the load, it is not constant. Ripple frequency, the frequency is 2 times. The average output will be 2 V naught by pi or 2 I naught by pi for one positive half. The efficiency of this thing will be 81.2. It is double the efficiency of that half wave rectifier. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. Since I use the word filter there, what is a filter? Basically, what we had seen, the output that you get is a combination of AC plus DC. So what do? To get the steady DC output from the pulsating voltage, a capacitor is connected across the output terminals. You can see a capacitor here which is connected across the load. You can also use an inductor in series with the load, but here we have shown it with a capacitor. So what happens? In the input, you have a AC. Because of this rectifier, which is a half wave rectifier or a full wave rectifier, you might get a fluctuating DC. Once you put a capacitor, you will get almost a current of constant value. This is what we call as a filter circuit. Do we understand this?
Yes, sir.
So a filter circuit is nothing but a capacitor connected in parallel. You can just note it down. So we now move on to another type of full wave rectifier, which is known as a bridge rectifier. Here 4 diodes are used. In positive half cycle, if you say D1 will conduct, then the current will flow like this. Do you see this? Then D4 will conduct and the current will come like this. Do we understand what is happening here?
Yes.
Everyone understands? In the positive half cycle, D1 and D4 are conducting. Do we understand this?
Yes, sir.
What happens in the negative half cycle? What happens in the negative cycle?
D2 and D3 are.
D2 and D3 are going to conduct. No matter what happens, I will show you. In the negative half cycle, this will become positive and this will become negative. Yes or no? Do we understand this?
Yes, sir.
So current goes like this: jig 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 jig. Do you see this? Jig 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 jig.
Yes.
D1 and D4 are conducting in the positive cycle and D2 and D3 are conducting in the negative half cycle. Everyone understands this?
Yes.
You have 2 minutes to note down the answer. And these are certain definitions that may come. If they come, you must be knowing what they mean, otherwise you will not be able to solve any question. The first one is known as the form factor. I think we have dealt with this form factor before. Form factor is RMS value divided by the DC value, whether it is for voltage or whether it is for current. Do we understand this? For a full wave rectifier, my dear friend, for a full wave rectifier, you can see the RMS value is I naught by root 2 and the DC value is 2I by pi. For a half wave rectifier, RMS value is I naught by 2 and DC value is I naught by pi. If you divide it, form factor for full wave rectifier will be coming as pi by 2 root 2, and form factor for a half wave rectifier would be coming as pi by 2. We understand this? Yes or no? We understand this? Yes or no? We understand this? Yes or no? Either we understand it or we don't understand it.
Understood, sir.
Okay. Ripple factor is the basically it's the ratio of how much current is AC and how much current is DC. So IAC divided by IDC. Total current, the RMS value of total current is under root of this. What you have to remember here is the ripple factor can be written in this form. I RMS square divided by I square DC minus 1, or it can be written as form square minus 1. If you put all these values together, you will get the ripple factor for a full wave rectifier as 0.48 and ripple factor for a half wave rectifier as 1.21. What you have to remember is the definition of this one, the definition of this one, the definition of this one, and the definition of this one, and the value of total RMS current. For half wave rectifier and full wave rectifier, you must remember the RMS value and the DC values. If you know this, you should be able to calculate any one of this. I'll give you a minute to note it down. Then this is a diagram showing the frequencies. These diagrams have come in question and they can definitely come as question in your attempt. For a half wave rectifier, if your input frequency is 50 hertz, this is the input frequency, the time taken to complete one cycle. Output is also 50 hertz because we have one half cycle, then the other half cycle is missing, so the frequency remains same. But in the case of full wave rectifier, the frequency becomes twice. Do we see this?
Yes, sir.
A minute to draw these diagrams. If we talk about in terms of pulses, here you can see there are two pulses, yes or no, but in the output you only have one pulse. We understand pulse?
Yes.
Here you have two pulse in the input and two pulse in the output. So remember, they can ask a question on anything. You have 1 minute to note this down. So here we have a complete one column, one table description of everything. Number of diodes, 1, 2, 2, 1, 2, 4. Do we understand center tap, that first one?
Yes.
The rest are the value RMS current. Here it is I naught by 2, it is I naught by root 2, it is I max by 2, and all these things are given. This just given in one table. If you want to keep them at one place, just write it in the form of a table. I'll give you a minute to note it down. Then we come to some special types of diodes, and these questions have come in exam many times. The most important one of these is a Zener diode, is a voltage regulating device. Just have to just write down the important voltage regulating device. Means it tries to develop a constant voltage, and this constant voltage is the breakdown voltage or the avalanche voltage. This Zener diode is always operating in the reverse bias condition. In the reverse bias condition, if the reverse bias is increased, we get a breakdown voltage or Zener voltage or avalanche voltage. When this avalanche voltage is reached, no matter what you do, the voltage remains constant. Yes or no?
Yes.
This device is now known as a Zener diode, which operates in the avalanche range, the Zener voltage or the breakdown voltage. It is used as a voltage regulator to keep a constant voltage. It is always in the reverse bias. In the forward bias, it just behaves like a simple diode, but we don't use it at a forward bias. We use it at a reverse bias to regulate voltage. This is the symbol of a Zener diode. It is always in reverse bias and it will keep voltage constant. That means the voltage across this point Vz, which will be the Zener voltage, that voltage will be applied across the load resistor. Do we understand this? Yes
Yes,
or
sir.
no? Do we understand this?
Yes, sir.
You have 2 minutes to note down the important points, draw the diagram. Okay, then this brings us to an end of this class. We are done with almost all types of diodes. We'll be seeing a couple of more diodes and we'll be solving a couple of more questions, and then we'll be moving on to the next part of this chapter, which is you now see PN. Now we'll put one more, so it becomes either NPN or PNP transistor. So we will deal with those transistors in the next class. We'll also see some interesting questions and we'll try to solve questions on the previous year. So I'll see you tomorrow. If you have any doubts, you can always ask me those doubts. Take care and God bless all of you. Bye bye.
Thank you, sir.